Hello, everyone. Today, we are going to learn about the design of mineral mixture composition. The design of mineral mixture mixed proportion composition is referred to as the mineral aggregate composition design, and it is to determine the proportion of each aggregate in the mixture. Currently, the design methods of mineral aggregate composition mainly include trial calculation and graphics. Let's learn the trial calculation first. It is only suitable for the combination of 3 to 4 mineral aggregates. Larger errors will occur with too many aggregates. Mastering the method requires mastering two hypotheses first. First, the sum of the proportions of all aggregates in the mixture is equal to 100%. For example, if mixture M consists of aggregates A, B, and C, and aggregate A accounts for 50%, or X equals 50, and aggregate B accounts for 30%, or Y equals 30, then what is the proportion of aggregate C? As the sum of the proportions of A, B, and C is 100, then the proportion of C is 100 minus 50 minus 30 equals 20. That is 20%, denoted as Z equals 20. Here is the second hypothesis. Suppose that the required content of a certain grade of particle size I in mixture M is AMI. For example, if the mineral mixture for asphalt concrete AC-13 requires that the proportion of 4.75 millimeters particle size in the mixture is 21.8%, then AM, or 4.75, equals 21.8%. The contents of this particle size in aggregates A, B, and C are alpha AI, alpha BI, and alpha CI respectively. For example, mixture M is composed of aggregates A, B, and C. The content of 4.75 millimeters particle size in aggregate A is expressed by alpha A 4.75 and so on. Then the formula is as follows. Alpha AI times X plus alpha BI plus alpha CI times Z equals alpha MI. For example, mixture M consists of crushed stone A, stone chips B, and mineral powder C. In mixture M, aggregate A accounts for 50%, or X equals 50. Aggregate B accounts for 30%, or Y equals 30. And aggregate C accounts for 20%. Z equals 20. If the crushed stone itself has 4.75 millimeters particle accounting for 52%, or alpha A 4.75 equals 52%, stone chip B itself has 4.75 millimeters particles, and the content is 2%, recorded as alpha B 4.75 equals 2%. Mineral powder C itself has 4.75 millimeters particles, and the content is 0%. Recorded as alpha C 4.75 equals 0%. Then, the content of 4.75 millimeter particle size in mixture M is 50% times 52, plus 2% times 30, plus 0% times 20 equals 26.6%, which is recorded as AMI and is 26.6%. After having mastered the two hypotheses, we can start the calculation steps. In the calculation, we should first pay attention to this. Grasp the big and small. What does this mean? It means that among all kinds of aggregates, we first focus on the coarsest and finest aggregates. Among them, we find particle sizes I and J of a certain grade with the most dominant content respectively. Firstly, it is assumed that particle size I only exists in the coarsest aggregate A. Then we can form the formula alpha Mi equals X times alpha Ai content of particle I in mixture Mi equals dosage ratio X of aggregate A multiplied by the content of particle I in A, then X equals content of particle I in mixture Mi divided by the content of particle I in AAIX equals alpha Mi divided by alpha Ai times 100. Similarly, it is assumed that the particle size J exists only in the finest aggregate C. So the content of grain size J in mixture MAMJ equals dosage ratio Z of aggregate C multiplied by the content of grain size J in C, alpha MJ equals Z times alpha CJ, then Z equals content of grain size J in mixture MAMJ divided by the content of grain size J in CACI. Z equals alpha MJ divided by alpha CJ times 100. Let's take an example below. The table shows the screen residue of aggregates A, B, and C. And the required gradation range of the mixture is as follows. That is to say, we use aggregates A, B, and C for batching to enable the gradation range of the mixture to meet the requirements of the standard. So, what is the appropriate proportion of aggregates A, B, and C? In the first step, let's first observe which aggregate is the coarsest and which aggregate is the finest among the aggregates. Obviously, the stone is the coarsest and the mineral powder is the finest. In the second step, which particle size is dominant in the coarsest aggregate A? Obviously, the screen residue on the 4.75 mm sieve is 50.5%. That is to say, the particle size of 4.75 mm has a predominance. Similarly, in the finest aggregate C, the screen residue on the sieve smaller than 0.075 mm accounts for 86.8%. So, particle size less than 0.075 mm is dominant. In the third step, calculate X and Z according to the formula. X equals alpha Mi divided by alpha Ai times 100. Dosage ratio of aggregate A equals required content of 4.75 mm particle size in mixture M divided by the content of 4.75 mm particle size in aggregate A. Column 1 in the table is the percentage retained, representing the content of 4.75 mm particle size in aggregate A. But column 5 in the table gives the cumulative percentage retained within the required gradation range for mixture, not the required percentage retained, and thus we need to do the translation. First, from the cumulative percentage retained of the gradation range, we calculate the median passing percentage P, equal to the average value of the lower and upper limits of the gradation range. Take the 13.2 mm mesh as an example. The median cumulative percentage retained equals 95 plus 100 divided by 2 equals 97.5. The second step is to calculate the median accumulated retained percentage A from the median cumulative percentage retained P. Since their sum is 100, then A can be obtained by subtracting P from 100. For example, the median cumulative percentage retained of the 13.2 mm mesh is 97.5, and 100 minus 97.5 equals 2.5 is the accumulated residue of the 13.2 mm mesh. The third step is to calculate the percentage retained alpha I of a certain particle size by subtracting the accumulated retained percentage A, I minus 1, of the previous particle size from the accumulated retained percentage AI of a certain particle size. For example, retained residue of 13.2 millimeters equals accumulated residue of 13.2 millimeters, 2.5 minus 16.0 millimeters, 0 equals 2.5, and retained residue of 9.5 millimeters equals 21 minus 2.5 equals 18.5. So far, we have figured out that the percentage retained of 4.75 millimeters and less than 0.075 millimeters in the mixture is 21.0% and 6.0% respectively. Then we can calculate X and Z. Substitute it into the formula and divide the retained residue, particle size 4.75 millimeters in the mixture, by the retained residue, particle size 4.75 millimeters in aggregate A, to obtain X equals 41.6% and Z 6.9% in the same way. Since X plus Y plus Z equals 100, we can easily figure out Y equals 51.5%. Then, the preliminary determined mineral mixture composition design is calculated as X equals 41.6%, Y equals 51.5%, and Z equals 6.9%. Let's carry out grouping according to the calculated proportion to see whether the composite gradation of the mixture meets the range in the standard. The first step is to list the original percentage retained on sieve of stone, sand, and mineral powder as follows. The second step is to list the proportion X, Y, and Z of the three materials in the mixture as 41.6, 51.5, and 6.9 respectively. The third step is to calculate the percentage retained on sieve of each particle size of the materials in the mixture. For example, the percentage retained of stones with a particle size of 13.2 millimeters is 5.2% times the proportion of stones is 41.6% equals 2.2%. In this way, calculate the percentage retained of each particle size in the aggregate in the mixture. Therefore, the fourth step is to add the percentage retained on the sieve for each particle size of aggregate in the mixture. For example, if pebbles with a particle size of 13.2 millimeters account for 2.2% in the mixture, and neither sand nor mineral powder contains stones with a particle size of 13.2 millimeters, then the percentage retained residue on sieve for aggregate with a particle size of 13.2 millimeters equals 2.2%. Similarly, the percentage retained residue on sieve for aggregate with a particle size of 9.7 millimeters equals 17.4%. The percentage retained residue of the mixture with a particle size of 4.75 millimeters equals 21 plus 0.8 equals 21.8%. Then, the accumulated retained percentage and cumulative percentage retained of the composite gradation are calculated. Finally, in combination with the cumulative percentage range required by the specification, a chart is drawn to judge whether the composite gradation is within the given range of the standard. Draw a diagram with cumulative percentage as ordinate and mesh size as abscissa, and then draw the upper limit of gradation range, lower limit of gradation range, and composite gradation curve respectively. If the composite gradation curve falls within the gradation curve range and is centered and smooth, it meets the requirements. If it exceeds the gradation range or is jagged, it needs to be adjusted. Calculate the composite gradation according to the above calculated mix proportion. If it is not within the required gradation range, adjust, recalculate, and review the mix proportion several times until it meets the requirements. If it cannot meet the gradation requirements after calculation, some single-size aggregate can be added or other original aggregate can be replaced. Well, today we learned the design method of mineral mixture composition trial calculation. Pay attention to mastering two hypotheses and the strategy of grasping the big and small. If the calculated composite grading is not within the required grading range, it shall be adjusted. That's all for today. Thank you.